ask Hamish the questions. Go ahead, Bert.
So you talked about that we can't talk about atomic resolution mapping.
Right.
And the detector has the maximum efficiency when we are just near about a zero tilt system.
About
Zero tilt.
zero. Oh, yes.
For a super X detector.
Yes,
Yeah.
Bricks.
But what is the case when we need to have a particular orientation?
Good question. Good question. Okay, so let me rephrase the question. So we talked about, can you do an atomic resolution map? I would not call it an atomic resolution. I would call it a channeling map. So first of all, because what we're doing is we're seeing channeling in the solid. In order to get channeling in the solid, all of those high resolution, atomic resolution channeling maps are done on zone axes. Okay. If you tilt to a zone, if your sample is not, if you have to tilt your sample to get to the zone axis, can you still do the results? The answer is, can you still do a map? The answer is yes. Realize that some of your detectors may not be working very efficiently. And in fact, some of your answers may be actually giving you garbage or noise. So what you should do in that case is figure out how you're going to tilt. If two of your detectors, in the case specifically for your system, you've got 4 detectors. And let's assume you tilted toward 2 of them, and 2 of them are getting very bad signal. They're actually going to give you noise. What you want to do is turn those detectors off. Okay? You can turn them off in several ways. Literally, I'm not suggesting you unplug them, but look at the software. Some of the software will allow you to disconnect and not display those. Or some of the software will actually allow you to acquire all the data but not display it. Okay? So can you do that? Yes. The other thing is to get a different geometry of detector. Now, you don't have the luxury of saying, I want to change my detectors on this microscope. But you may have a colleague that has a different system. Okay? And for the Super X system, the nice thing is it's maximized in efficiency near flat. Other systems are maximized somewhere else. Okay? The JOL geometry is different. The picoprobe geometry on my machine is different. I can actually do, I didn't show you a tomogram. I can do tomographic maps, or tomographic hyperspectral images from which I can get an elemental map. And you have to just do it very carefully and very slowly. Okay? But again, don't call them atomic resolution. The other thing I neglected to say, and I'm glad you asked that question because you now reminded me I didn't say it. Never, I showed you examples of channeling in solids. One of the things I never showed you, and I forgot to mention, is when we try to do quantitative analysis, we never do quantitative analysis on a zone axis. Okay? The reason is, to do quantitative on a zone axis, you have to do the full dynamical calculation of the wave field going through a solid. You should always tilt off the zone axis by about 1 or 2 G, 1 or 2 diffracting vectors. And then you wash out the channeling effects, and then the quantitative analysis equations that we talked about apply. Okay. So we said, in EDS, we said no energy loss, no absorption, no fluorescence. I should have also said no channeling. Okay. So go away. Never try to do quantitative analysis in strong channeling conditions. Can you? Yes, but to do it right, you have to do all of the calculations. Most of the time, the calculations are pretty extensive. Can be done? Yes. But it's easier just tilt away from the channeling conditions. Okay? Anybody else?
I have another question.
Oh, go.
So by limiting the apertures in a image corrector system, which doesn't have a probe corrector, we improve the resolution of the stem map.
Yes.
But we are reducing the quantity of EDS signals we collect.
Right.
So what could be a good combination, and how to know that we are not losing enough EDS signals, but we are able to go to a nearly good resolution?
You're talking about the apertures?
The condenser apertures.
Yeah, so the condenser apertures controls,
Condenser apertures,
yeah, he's talking about the condenser apertures controlling the amount of current.
Items.
Yeah, So, and so controlling the convergence angle, and he wants to put in, where's an optimum, is what you're asking. Is a bigger aperture better than a smaller aperture?
It's a ratio of the below rate.
Well, there's two apertures, but he was specifically asking about EDS, not ELs, right?
EDS, yes.
ELs.
EDS.
Oh, EDS. So in EDS, I would actually go for the bigger aperture, okay? What I would go for the bigger aperture because you will average out some of the dynamical effects. But more importantly, what you worry about is how much beam current you're putting on the sample. So what I would try to do on your system is make sure your system is calibrated so you know how much beam current you're coming in, because what you'll need to do is not worry about just how much beam current's there, but what your sample is. So the amount of beam current you can put on a metal is orders of magnitude more than you can put on a polymer. Okay, so you can put a nanoamp on a piece of metal and it'll still survive. You try to put a nanoamp on a polymer, you'll burn it instantly. Okay, so now what I do is I've standardized my system. I've calibrated my screens so I know how much beam current I have under different conditions. And I know for the kind of samples that I deal with and the amount of analysis time when I start destroying them or not. Okay. I'm lucky. I've got a very efficient detector. I can run at 100 picoamps of beam current and get plenty of signal both for imaging and for spectroscopy, both EDS and ELs. Okay. In a less efficient system, you're probably going to have to go toward from 100 picoamps to maybe 500 to maybe even as much as a nanoamp. Be very careful when you start getting up to a nanoamp on many materials because you'll start destroying them. Okay. 100 picoamps, even 100 picoamps is a lot, particularly for a polymer. That's a huge current for a polymer. In a polymer, I'll probably drop down to 30 picoamps at some time. That's not a lot of signal. Okay. All right.
If I may, I have another.
Cool.
On a subject which we have not touched thoroughly, it's basing on the Ronchigrams.
Oh, Röntgengrams. Okay.
So for amorphous material, it's pretty clear. But how does it vary when we go to a crystalline sample?
Ooh. The question is, what do you want to do with the Röntgengram? You want to focus?
Yes.
Okay.
It doesn't have much of amorphous.
Yeah. All right. You still, let's see now. Let me see if I have an example of that. I'm gonna look. I remember having an example of some Röntgengrams. Röntgengrams, yes. Röntgengrams. Open. These are some examples that I borrowed from a colleague in Australia, if I can find them. Where the hell are they? I'm looking for them. Hold on a sec. Maybe they're further down. Ah, there we go. Okay, actually, oh, they're from Dave Muller. Okay, I got them from, all right, so this is what a Röntgengram looks like. It's 000 disc in stem, and what we're illustrating here is how we do a little bit of aberration correction, because a Röntgengram, when it's perfectly focused and we got the beam in focus, is a nice round circle, okay? And when it's aberrated, we have ellipses. Okay, you can see the ellipse that way, the ellipse that way. The way we astigmate in an amorphous sample is we can make that round. Now, what you asked is, that's for an amorphous sample. How do I do it in a crystalline sample? Okay, what you have to do is, and this is something you're going to have to learn how to do as you go through focus in whether it's a crystalline material or an amorphous material. you will still see this thing expanding and decreasing its size. You'll go to the point that's called infinite magnification, okay? And the only way to show you that, I probably should, that's a good thing, I'll have to add some slides like that. You'll have to learn on your sample how to go to infinite magnification. And you'll see the image zoom in and zoom out as we go in and out here, okay? See if there's another one. I don't think I have a better example of that. Oh, yeah, here we go. Here we go. So as we under focus, we go toward focus, you'll see an image here. You actually have an image of your sample. Even if it's crystalline, you'll see something. And as we go through focus, this thing will begin to blow up, okay, and you'll get to what's called the infinite magnification site. The only way to demonstrate that is to actually see it in line. It's hard to show it on photos, okay? In a crystalline sample, you literally see dots, which are images of the atoms coming up, okay? The only way to do that is to actually just sit down and do it. Reminds me, that's a good point. Maybe I should make a movie of that and put it in here. Okay. But there's no other way other than just sit, watch it, and go in and out of focus. And as you go in and out of focus, you'll see the image. Far enough out of focus, you'll see a low magnification image. And as you go toward focus, it'll start increasing, and you'll actually see a transition. It'll go through a crossover and then go the other direction. Okay? All right. All right, so we should try that. I think that's the best. We should just try to do it and have a look at it. All right. Any questions for Hamish? Okay. I apologize for losing my voice. I apologize for trying to cover more material than I should have. The notes that you have a lot more in it than what I talked about. Feel free to page through those, and if you have some questions about some of it, there'll be topics in there that we just didn't have time to cover. There's topics on radiation damage. There's topics, information on other stuff. We just didn't have talk about it. There's lots of things on channeling and alchemy and the like. I think what we were overly optimistic on what we would cover. Just a bit. If we do it again someday, we've got to either make it longer, more days, or focus in a little bit narrower. So, for example, we probably could have spent 3 days just on EDS and EOS. Okay. Okay, I'm losing my voice again, so I need to stop. Thank you all again for your attention. You need to thank Hamish. All right. Bye, everybody online. Oh, Senator Guns wants to say something. Oh, okay. Oh, we got one more thing. Okay. One more person to say hello and goodbye. I need some more water, so excuse me. Where's my bag? No, I water in my bag. I brought extra. Yes. Question? Yeah, ask a question. Camera's still running. Ask it.
Yeah. So you're preparing a sample for these flexipolymers or biological tissues.
Yeah.
Can you suggest different ways of embedding it in epoxy and trying to cut it?
Okay, so the question was on sample preparation, which is a whole topic we didn't talk much about. And that's several lectures there. The important thing and our colleague, and I apologize, I don't know your name. He's got a polymer that he wants to look at. So how do we look at a polymer? How do we prepare a polymer? Okay. In his case, give me your sample. So what? I don't know. Do you still have the plastic? Yeah. What his particular problem is? There we go. That's good. You can almost see it in the white bag. Okay. He's got basically a plastic with silicon in it, right?
Yeah, silica with polyethylene.
Okay, silica. Now, how do you prepare a sample of this to put in the electron microscope? If you just put this in, you're not going to never see through it. What you need is a thin film through here, right? So what he's done is he's taken a small piece of the polymer with the silica in it, embedded it in an epoxy, okay? We're going to then take that epoxy and put it in a device called a microtome, which is basically an ultra-sharp knife, and make thin slices of it, okay? We'll then float that on top of a copper grid and try to put it in. Now, the challenge with his samples is going to be, you're going to want to do a cross-section through this, right? So what you're going to, can we write on the board? We have a writer? Yeah, hang on. Writing utility. Here we go. All right, so he's got a thin polymer, thin film. He's going to embed it in an epoxy capsule, okay? And then what we want to do is make a thin slice through it, to make that thin slice so we can look through it. So what he's going to do, he's going to cut it so it looks something like that. And then he's going to take an ultra microtome, a diamond knife, and make thin slices. Those thin slices are going to look like small sheets. Going to pick them up on a copper grid, that sheet on there, and put it in the microscope. The challenge that he's going to have is, because this is a polymer, he's got to learn what the beam conditions are right so you don't destroy the polymer. I specifically picked that one example of polymers for you because that was a dual polymer of polystyrene and PMMA. And the PMMA is electron sensitive and the polystyrene is not. So I'm not sure what polymer you have. Yeah, so I don't know how beam sensitive that one is. But more importantly, what he really wants to do, and correct me if I'm wrong here, you wanted to image the silica particles in the polymer. All right. So the trick here is you now have, and what I'm going to recommend for your particular experiment is, because you know you have silica in carbon, okay? What's the atomic number difference? Silicon is 13, carbon is 6. Good atomic number difference, that's 7Z. A STEM image in high angle dark field will show up the silicon and the carbon will not. You won't have to do a map, okay? I would just do a simple high angle dark field image of the silicon, and the silicon will be bright and the carbon will be darker. So that will be the easiest way for you in this material to do the map. If all you're interested in is where's the silicon, that's the easiest. You don't have to do EDS, you don't have to do EEL. I would do EDS and EELs anyway just to make sure the silicon is there, but you don't need to do an EDS map. All you want to do is say, what's the question you're asking? Remember, that was always our point. What's the question? Where is my silica? Okay? The question is, where's my silica? What signal do I need to measure to show the silica is there? So, do you do EDS to find out, to make sure you have silicon in there? Yes. Good. Now, is the STEM high-angle dark field signal strong enough to show you where the silica is? Yes, because you have silica, atomic number 13, in a matrix of 6 carbon. So just do a EDS first to make sure silicon's there, and high-angle dark field to show the distribution, and you're done. Simple experiment, in theory.
Don't take your time.
Yeah, don't take your time. All right. Yes, and what you want to try to do, so he's asking how to mount the sample, and what I would, specifically for yours, I would mount your entire sample in like as straight as you can, okay? And embed it in your epoxy. Then slice, you're learning how to do the microtome, so you know you're gonna have to slice a little bit, but you want to do the slices this way. So you want it this way, not flat, okay? All right. I think we're done now.